So let me share the screen with you. Okay. So in the last class, we were in lecture 17, where we looked at the boundary conditions, and we got two boundary conditions. One is the the tangential component of the magnetic field is continuous, is equal to the surface current at the interface, and second is the normal component of the magnetic flux density is continuous at the interface, and these were obtained from the Ampere's law and from the Gauss's law of magnetic field. And we looked at an example how we can apply the magnetic boundary conditions to both an interface which is carrying a surface current and the interface which is charge free. And we also looked at how to find the angles of the magnetic field vectors if the angles and the magnitude of the vectors are given to us. I think this is what we did it in the last class. Okay, so now today we are going to go for the next topic of our course, and that topic is on inductors. Okay, so yes, I told you that, you know, the poll question, I just wanted to check with the poll question. Yes. So if you see, guys, see, this is what I told about the poll question. Just a second. Yeah. See here. See here, what is the magnetic force? Okay. So please, you know, you need to retain the material that we are covering. Okay. And that is one of the objectives that I'm trying to ask 1 to 2 questions from the last 2 classes. You need to, you know, remember. So see, just look at the formula. So the formula is clearly telling us that if my charge is moving with a velocity of v, if u, in an external field B, then my force will not be in the direction where the charge is moving. That means it will not be in the direction of u. See, it is u cross B. So that means it will be in the direction perpendicular to both u and B. It's the electric force. Yes, the electric force is correct. So if a charge is moving with a velocity of u and in the presence of an electric field, then the force will be along the direction where the charge is moving. And also, it's not at all related to the velocity, because it is just, see, in the expression there is no u. So it doesn't depend on the velocity as well. It just follows E, because your charge, wherever is your electric field, along that direction your charge will be moving, if it is a positive charge. If it is a negative charge, then the force will be negative and it will be moving in the other opposite direction. Okay, so you know this thing, please try your best to, you know, review and practice, because we have our midterm exam, you know, just say how many, I think 10 days down the road. So please. Okay, so today we are going to do inductors and inductance. Okay, before that, let me just have a poll of the last, sorry, this is wrong. Let me have the poll of the last class, magnetic boundary conditions. Very simple. Okay, the first question. Start. So magnetic boundary conditions were derived from, so select whichever is appropriate. Ampere's law, Gauss's law of magnetic field, both the above laws, or magnetostatic vector potential. You have 20 more seconds. We just did it in the last class. We reviewed now also. 5 more seconds. 2, 1, and that's it. So I think, most of them have put it correctly. It is both the laws. These one, both, not just one, both. See, both the above laws. Why? Because Ampere's law gives you the tangential component relation, and Gauss's law of magnetic field will give you the normal component of the boundary condition, the normal component of the magnetic field. This is the tangential component, this is the normal component. Okay, so stop sharing. Last question, again, this is on the magnetostatic boundary conditions. Very simple, true or false? Magnetostatic boundary conditions states that the normal components of the magnetic flux density, oh, sorry, it has to be B, not D. B are continuous at an interface separating two mediums. B for bat, it has to be B. "15 more seconds. 5, 4, 3, 2, 1. Okay. This is good. So at least you remember this. So 89% said is true, and the correct answer is true. Yes, the normal components of the magnetic flux density is continuous across the two interface separating the two mediums. Okay, so now let's start the inductors. So what does the inductors topic says? This we are going to cover today, and that is the objective of today's class. So we are starting with a simple argument, and it is saying that we have two loops. So we have two loops here. This is one loop which is carrying current I1. This is another loop which is in close vicinity of the first loop, which is carrying current I2. So I1 and I2. Then this current I1, which is passing in this loop, will create a magnetic flux density. Agree? It will create a magnetic flux density because it is carrying a current and it is in the loop. And if you remember, no, the expression is here, I will show you. So it will generate a magnetic flux density B1. And this loop, the number one loop, has n turns. Then what is our argument? So our argument is saying something like this. We know that the magnetic flux density, which is generated in this by this loop 1, is proportional to the current passing in this loop, right? It has to be, because this is the source of this magnetic flux density. Because of this current passing, you have this magnetic flux density. And this is coming from the Biot-Savart's law. See, the current is the source which is creating this magnetic flux density, which is B1 is mu integral over L I1 dl cross R over 4 pi R cube. So that's why I'm saying B1 is proportional to I1. Now, this magnetic flux, which is now everywhere. See, this magnetic flux B1, magnetic flux density B1 is everywhere. Now, this magnetic flux density will create a magnetic flux through this circuit number 2, which is in the vicinity of the first current loop I1. So there is a current loop here. Okay, And it's just a current loop, nothing. Current is flowing in loop 1, not in loop 2. So just a loop is there. Then there will be flux through this loop, right? How can you find the flux through this loop? It is nothing but your psi 21. And what it will be? So it says that the flux through the second circuit or the second loop due to loop 1 is nothing but integral of, so what is the magnetic flux density which is flowing here in this loop, flowing around this loop number 2? It is B1, because B1 is now everywhere. So it is B1 dot ds2. ds2 is nothing but this, the cross-sectional surface, this cross-sectional surface. This cross-sectional surface. This is your ds. This is your S2. Okay. So again, there is a current I1, which is creating a magnetic field, yellow color magnetic field everywhere. Okay, this is B1. And I'm now finding the flux through this loop number 2, which has N2 turns. And how do you find the flux? I know flux is integral of B bar dot ds bar. So now I'm saying it as psi 21, that is flux in circuit 2 due to circuit 1 is equal to integral. What is the magnetic flux density? The magnetic flux density of the the magnetic flux density which is in this region. And this magnetic flux density is nothing but the magnetic flux density created by the, or generated by the loop 1, and integral over this surface, closed surface, which is the black one. Okay, so this is called the flux. So this is the flux through circuit 2. So flux through circuit 2 due to current in circuit 1. Now I'm using the terminology. Please be, understand the terminology. So the terminology is, this is the flux in 2 due to 1. That means the flux in circuit 2, due to the current in circuit 1, because the current is generating B1, and with the help of B1, we are seeing this flux here. So I can say that the flux is proportional to B1 and is also proportional to the current I1. That means the flux in circuit 2 due to circuit 1 is proportional to I1. So this is my argument. It is proportional to I1. Now, what I am doing here, I am now defining a flux linkage, which is very, very well known. Flux linkage is nothing but psi 21 is the flux in the second loop. But if the second loop has n turns, then we define it as flux linkage, which is nothing but just the multiplication of the number of turns with the flux. So the flux linkage, this is called as uppercase lambda. So flux linkage in circuit 2 due to circuit 1 is equal to the number of turns of the circuit 2, which is N2, times the flux in circuit 2 due to the circuit 1. So it is N2 psi 21. So therefore, now what I can say is the flux linkage of circuit of loop 2 due to loop 1 is proportional to the flux 21, and this flux 21 is proportional to B1, and B1 is proportional to I. That means your flux linkage of loop 2 due to 1 is proportional to the current flowing in the first loop. And this proportionality, I'm removing it by putting a proportionality constant, which is called as M21. So uppercase lambda, that is the flux linkage to 1, is M21 times I1. And this M21, which is the proportionality constant, is called as the mutual inductance, and its unit is Henry. Okay, so this is the expression, and therefore I can find it as the flux linkage to 1 divided by I1. Now, if I write flux linkage to 1 as N2 psi to 1, so that means it is N2 psi to 1 over I1. It is nothing. This is the mutual inductance. Okay, so therefore it is the mutual inductance in loop 2 due to loop 1, due to the current passing in loop 1. This is the expression. So this is the argument when the current is flowing in I1 and we are experiencing in loop 2. The other way around is also possible. That means, suppose if I pass current in loop 2 and see what is the flux linkage in loop 1, yes, I will get the same. I will get the same phenomena. That means I will get the flux here, which is now termed as 1, 2. And if there are N1 number of turns, then I will get the flux linkage. And then from there, I can get the mutual inductance. And here the mutual inductance is M12. That is the mutual inductance of circuit 1 due to the current passing in circuit 2, which is the flux linkage of 1, 2 over I2. And the flux linkage of 1, 2 is number of turns multiplied by the flux. So psi 1, 2 is flux through loop 1 due to loop 2, or due to the current passing in loop 2. Okay, so these two are called as mutual inductance, and then from energy conservation we can prove that both are equal. M12 is M21. Okay, but proving this is out of the scope of our course, so we will just take this. So these mutual inductance, either here due to the influence of, either here due to the influence of this one, or here due to the influence of this one, they are the same. Now, similarly, we also define two more types of fluxes, because we just now saw psi 1, 2 and psi 2, 1. We can define two more type of fluxes, which is called as psi 1, 1 and psi 2, 2. Psi 1, 1 and psi 2. And what are these fluxes? These are called self fluxes. So what do you mean by self fluxes? What do you mean by psi 1, 1? Yes, Mr. Abdul Rauf Ibrahim, can you tell me? Now, what does the psi 1, 1 represents?
I don't know.
See, how we defined psi 1, 2. Okay, Ibrahim, tell me what is psi 1, 2? What happened?
Dr. Min Ibrahim Shamasi?
I said Abdul Rauf Ibrahim.
Yeah, Abdul Rauf. Yes.
Yes, you tell me. Just now we learned about these two, right? So,
Yeah.
you know, just tell me, just repeat what I said. What is the psi 1, 2 and psi 2, 1? Maybe someone else?
Yes, Doctor.
I think who raised the hand?
Yes, Abdul Majid.
Yes,
we
Abdul
write
Majid.
the effect of the effect in 1 due to 1, the self-inductance.
Yeah, yes. So see, the same, you know, same analogy that we used here. This is psi, that means flux in the first loop due to the current passing in the second loop. This is psi in the second loop due to the current passing in the first loop. Here, psi in the first loop, that is flux in the first loop due to the current passing in the first loop itself. So these are called as self fluxes. Here also the same thing, flux which is through my circuit in loop number 2, and who is responsible? The loop number 2, the current passing in the loop number 2 itself is responsible. that is called as self-flux. So if this is your I1, and if it has number of turns N1, then it will generate a magnetic field, right? Magnetic flux density, which is B1. This is I1, this is N1. So it is generating magnetic flux density. Now, if we integrate it over here, that is, if we find the flux through the same loop 1 due to the magnetic field or magnetic flux density which is generated by loop 1 itself, that is your self flux. Okay, not for others. It's same. So this is called as the self flux, psi11 and psi22. And based on that, we can get two more proportionality constants, which are this. So L11 is flux linkage 11 over I1, and which is flux linkage N11 is nothing but N1 psi11 over I1. So it says, what is this flux linkage 11? It is the number of turns of my first loop times the flux 11 over the current passing in the loop I1. And this is for the loop 2. And these are called as, so this proportionality constants, they are not M11 and M12. They are called L11 and L22 because they are called as self-inductance. So overall, we have 4 fluxes, psi12, psi21, psi11, and psi22. This psi12, psi21, they are affecting each other. That is, one loop of current is, or one loop is affecting the second loop, or the second loop is affecting the first loop. That's why it is the proportionality constant that we got from here is called as mutual inductance. Whereas this flux is self. That's why it is called as self-inductance. And these are the expressions that we can use to derive or to find the mutual inductance or self-inductance of any type of, loop, any type of loop. So here we are now taking an example of a solenoid. Okay, we are taking an example of a solenoid. So what is the example? The example is saying that we need to find the expression for the inductance of a solenoid. So if you see here it is not showing you whether it is self or whether it is mutual. Why? Because you have only one wire loop here. There is no other wire loop. So automatically it is referring to the self-inductance. So therefore, inductance, when we use the word inductance, it mostly represents the self-inductance. And until and unless the word mutual is used, so you're finding the self-inductance of a solenoid. So what are the steps to find self-inductance of any loop, which is any loop? So the steps are these ones. So first, you need to find, okay. First, you need to identify the coordinate system. So not identify, select the coordinate system. So select whichever coordinate system is applicable and easy for your analysis. So this is my solenoid, and please, the drawing is not good, but its cross section is circular. So the cross section is circular. Okay, cross section is circular, and the radius is A, and the area of this cross section is S, which is equal to pi A square. And on that cross section core, so this is the core, on that we are winding the wire. So what are the steps? First, identify the coordinate system. So for me, the best coordinate system is cylindrical, where I will place the center of my solenoid along the z-axis. Okay, so if I place it along the z-axis, then this will be my rho. Okay, this and this will be my rho. Now, after that, then what we need to do? What is the next step? Then pass a current I. So you pass a current I through this coil. So I'm passing a current I. So this is my current. I can pass my current I. And then find the magnetic flux density. And then find the magnetic flux density. So this is my current flowing. And I want to find the magnetic flux density coming out. Now we already did this. So let's quickly do it. If we use our hand, a quick review here. So the direction of the current is like this. If I quickly color my hand here. So my hand is my fingers showing the direction of the current curving. Then my thumb will show me the direction of the magnetic field, and therefore the direction is Z. So therefore B is my BAZ. Now only I need to find B, and we have already done it. That we already looked at this, and this is nothing but, just to recall, we got H as Ni times AZ. This is what we got it. We derived it in, I think, our lecture number 15. H is Ni times AZ. So therefore, B will be what? Because we want B here. So it is mu Ni times AZ. And mu is nothing but mu naught mu R Ni times AZ. And what is small n? Can anybody recall what is small n? Small n is called as turn density, which is nothing but how many turns it has? N turns. And what is the length of my solenoid? D. So it is number of turns divided by the length. So if I substitute here, so I get mu naught mu R Ni over D times AZ. This is what we have. And of course, remember, we are ignoring the field fringes. We are ignoring the field fringes. We are assuming that our magnetic field inside the core is constant. Based on that, we are deriving this. Now, this is the second step. Once you find the magnetic flux, the third step is to find the self flux. So self flux is psi 11. But sometimes we drop this in inductance because it doesn't matter. It is a self flux. So the self flux is nothing but integral over the surface b bar dot ds bar. And since my d is constant, so this will just be equal to what? So this will be just be equal to psi is equal to integral over the surface b bar dot ds bar. Now, what will be this surface? Can anybody tell me what will be this surface? We are integrating, through which surface? Yes, Mr. Saif, can you tell me? Saif al-Zahrani, can you tell me? What is the surface here? Saif, you are here or no? Zuhair, can you tell me what is the surface?
Surface.
Yeah, because you see, for the flux, you need to find the flux through a surface. So which surface it is? Saif, I can hear you. So which surface is this, Zuhair?
Let us see. If we're talking about this
Yes,
line,
Abdullah Ali, yeah, just give me a minute. So see, Now,
Okay.
let me draw it this manner. This is your core. Okay. And this is your windings. And this is your z-axis. Okay. And this is your rho. Or now tell me, how is the magnetic flux density? See, the magnetic flux density is along the z direction. So the magnetic flux density which is generated by this solenoid is like this. See? And it is only inside, it is not outside. Now I want to find the flux. So this magnetic flux density B bar, I need to integrate it over what surface? Now can you tell me?
Yes. So along that the surface is that circular base along the z-axis.
Yes. So it has to be integrated over this surface.
Yes.
Okay. And that's why it is B bar dot ds. But since my B is a constant, that's why I do not require an integration. I explained this, very well in the tutorial. So it will be just B multiplied by S, and therefore, what is your B? Mu naught mu r Ni over D times S. And what is your S? Is the cross-sectional area, which is pi a square. See here, it is already here, pi a square. So that's why this is your flux. And the flux linkage will be what? Since it has n turns multiplied by n, so this is the flux linkage. And once I got flux linkage, then the self-inductance is flux linkage over the current I. So if I divide this with I cancels, and this is called as the self-inductance. Mu naught mu r n square S over D. This is the self-inductance of a solenoid. And these are the steps. So first, identify the coordinate system. Second, pass a current and then find the flux density. Third, find the flux passing through the cross-sectional surface of your loop, or the surface which is enclosed by your loop. And once you find flux, then find flux linkage and eventually find the self-inductance. Okay. So here you have it for the toroid. So this I will do faster for toroid because it is very similar to solenoid. So for the toroid, and how is the toroid? The toroid, this is a little bit different because here the cross section of my core is not circular, it is rectangle in shape. And this is my toroid. And this is how the current is passing. See? This is how the current is passing in the toroid. And it is n turns. And this is the cross section. And by the way, guys, I'm sorry, this should not be close, it should be somewhere here. Because here also it is A and this should be B. So this is the cross section. Now, how do you do this? Same, choose the coordinate system. So for us here, the best coordinate system, as we have seen it while deriving its magnetic flux using the Ampere's law, it's the cylindrical coordinate. So I have put this Z, which is at the center, then pass the current and find the magnetic flux density. So this part I am not doing it because we have already done it using Ampere's law. So the magnetic flux, magnetic field is this one, Ni over 2 pi rho a rho. And remember, this is only in the core, because we have seen that the magnetic field cannot exist here and outside. The magnetic field only exists inside the core. That is when rho is between A and B, only this one. Okay, it exists only here. So therefore, magnetic flux density will be just multiplied by mu, which is mu naught mu r. This is your magnetic flux density. And once you know the magnetic flux density, find the self flux, which is B bar dot ds bar. And here again, if you see, you have the cross-sectional area. Now, what is the cross-sectional area here? Now, can anybody tell me what is the cross-sectional area here? Yes, what is the cross-sectional area? Anyone can say, tell.
Is it a rectangle, Doctor?
Yeah, this is the rectangle. See, this is our core, guys. See, our core is like this. And it is something like this. It is rectangular. Very difficult to draw. But, okay, maybe I can draw a part of it. It is something like this.
Is it to by
See, it is something like
R
this.
square?
See, I'm, no,
Multiply the length.
Cannot be 2 pi r square. I will tell you why. I'm showing the half of it. Okay. Okay. So I'm cutting it into half. So I'm cutting it from here and I'm showing you. This is how the core is. And your wire is on this core like this. Okay. Now, how is the magnetic field, magnetic flux density? It is A rho. That means if this is my z axis and this is my y and this is my x, then my A rho, how would be my A rho? My A rho, that is my magnetic flux density, will be going in this direction. Oh, I should not.
A5.
Yeah, A5, sorry. So it will be in this direction. So it will be going in this direction in the core. So in the core, it will be going in this direction. See? It will be like this. It will be like this and coming out from here. So this is your magnetic flux density. So your cross-section area is the rectangle. And now it is not uniform. This is what I wanted to emphasize. Look at my B. Is my B uniform? Is my B a constant? Is my B a constant? No. See here? It's not a constant. So I cannot say that it is simply B multiplied by S. And what is your S? Is the height of this rectangle, which is H, and the width of this rectangle, which is B minus A. No, it is wrong. The area is not H times B minus A. This is wrong because here your B is not constant. So therefore, what I can do is, yes, the vectors are changed into the scalars because A phi, and what will be your ds? Your ds for this yellow surface in cylindrical coordinates, your ds bar will be d rho dz a phi. D rho dz a phi. So when you dot product this with this, a phi dot a phi will be 1, and therefore you will have mu naught mu r ni over 2 pi rho times d rho dz. So now you have to evaluate the integral. Why? Because your b is not a constant. So I cannot take this outside the integration. Very important. I cannot take this outside the integration. So now I have to integrate. So d rho, what limits d rho is taking? D rho is this one, right? See, this is the d rho. Or I would say this is the d rho from here to here. So it takes values from A to B. So A to B. And dz, what is the height? From here to here, which is from 0 to h. Okay, from 0 to h. This is how you have to do it. And to make it much easier for you, you can, let's put this, this here. This is at the center. So this is your Y and this is your X. So therefore, your row will take, so this is your row. So it will take values from A to B. Okay. And then you find your psi. And once you know psi, then you can find the flux linkage. And from the flux linkage, you can find the self-inductance. Okay, you can find the flux linkage, which is this one. See, flux, this is the flux linkage, and then you can find the self-inductance. Okay, any questions here? Now, let us take one more example of mutual inductance. Okay, one example of mutual inductance. So if you see here, this is the example. The example is saying that you have two solenoids. If you see here, these are two solenoids. One is inside the other. So the inner solenoid is small. It is circular cross section and the cross sectional area is S1. The outer solenoid is larger. It has larger cross section and the larger cross section is S2. And the inner solenoid length is D1 and the outer solenoid length is D2. So this is my outer solenoid number 2 and this is my inner solenoid number 1. And my D2 is greater than D1 and my S2 is greater than S1. Now you need to find the mutual inductance between them. So how do you find the mutual inductance? So you have two ways. Either you can find M12 or you can find M21. Both will give you the same answer. So you need to decide. So should I find M12 or should I find M21? Now in this case, finding M12 is easier and M21 is difficult. And why it is? Think about it. Think about it, why it is the case. And maybe in the next class, if you remind me, we can just discuss for a couple of minutes why it is easy. So here M12 is easy. That is finding the flux in the first loop due to the current passing in the second loop is much easier. So therefore, we are going to use M12 as N1 psi12 over I2. So that means I'm now going to pass the current I2 in my second loop. So first identify the coordinate system. Again, it's a solenoid, so it is easy. So I can make the center as my Z axis. So therefore, this will be rho. Then once I am passing the current in the second solenoid, which is the bigger solenoid, first I will find its magnetic flux density. So the magnetic flux density is nothing but mu times H2, which is mu times N2 I2 AZ, because mu times Ni is the value. But here this is for the second loop. That's why it is mu times N2 I2. So mu times what is N2 is the number of turns. So if my second loop has turns N2 and my first loop has turns N1, then it is N2 over the length. Length is how much? D2. So N2 over D2 times I2 AC. This is the magnetic flux density. Then you find the flux. But which flux you find? Psi12. That is the flux in my circuit 1. Sorry, not circuit 1. In loop, flux through loop 1 due to loop 2. So integral flux through loop 1, that is the surface enclosed by loop 1. That's why I'm writing it here 1. Then B2, this is the magnetic flux which is there everywhere. And you're integrating it over the surface which is enclosed by the loop 1, ds. Now here again, you do not, this two will be, dot product will vanish and integral will also vanish, because if you see here, you do not have any variable here. They are all constants. In the previous example, you had rho as a variable. That's why you cannot take it outside the integral, but now you can take it. So therefore, this will simply become B2 S1, and B2 is what? Mu N2 over D2 times I2 S1. This will be the flux. And what will be the flux linkage? So the flux linkage will be just multiply by the number of turns of my loop 1, which is N1. And once I multiply by the number of turns N1, I will get the flux linkage of my loop 1 due to loop 2. And once I get the flux linkage, then the mutual inductance is uppercase lambda 1, 2 over I, which is mu N1, N2 over D2 times S1. This is called as mutual inductance. Mutual inductance. This is how you can find the mutual inductance. Okay. So think about it. You know, why we used M12 and why we did not use M21. Think from the point of view of this magnetic flux density expression that we used, and you should be able to get it, because this is the expression which is valid only within the core of the solenoid. We are ignoring the field fringes. So field fringes are ignored. Okay. So think from that point of view, you will get it. Now, the energy. So as in the electrostatics, the electric field can have an energy, which is the electrostatic energy given by half mu E square. In a very similar way, the magnetostatics can also store energy, and its energy density is given by half mu H square. In electrostatic, it is half epsilon E square. Okay. Here it is half mu H square. So this is joules per meter. This is for the electrostatics. And it is half mu H square. And if you want to find the energy, you can integrate this magnetostatic energy over any volume. Then you will get the energy. And also half mu H square is not the only way. There are other ways as well. See, so it is half mu H square or half B bar dot H bar or B square over 2U. Very similar to the electrostatics. It is half epsilon E square or half D dot E bar. Okay, so this is called as magnetostatic energy. Now, can we find the magnetostatic energy stored in a solenoid quickly? What will be the magnetostatic energy stored in a solenoid? We know everything. That's why it can be very quick. I know H. What is my H? See here, my H, because I don't need to worry about the vectors. It's an energy. So it is H is Ni, is the number of turns, is N, length is D. So N over D times I. So therefore, my magnetostatic energy density will be half mu H square, which is this one. And therefore, my energy stored will be, I am not doing any integrations here. I'm not saying integral over V small m dV. Why? Because if you see here, my H or my H bar is uniform. That is why. It is uniform. It's a constant. So automatically small m, the omega m can come outside the integration. And this is nothing but this value, and integral over V dV is nothing but the volume. What is the volume of this one? The cross-sectional area, which is S multiplied by the length. Okay, multiplied by the length. So it is nothing but S times T. The volume of a cylinder, pi r square L, or here it is A. So it is pi A square, which is S, multiplied by length, which is D, S D. And if you put omega small Wm here and then simplify, you will get that the magnetic flux density, the energy is equal to half Li square. And this is the expression we have been using in electrostatics. And here now you know how it is derived. So this is the energy stored in a solenoid. And it turns out that this is the expression that is valid for any shape of current, any shape of loop current, no, a loop carrying current, any shape. Okay, so I think we will stop here. And then in the next class, we will continue and we will try to wrap up this part and then take the next chapter. Okay. So thank you very much, guys.
Doctor?
Yes.
What is the material for the midterm?
It is not decided. We will tell you next week. Okay, during the weekend, we are going to discuss and we will let the students next week. Most probably it will be the electrostatics and the magnetostatics.
Thank you, Doctor.
Thank you. Okay, thank you very much, guys.